Welcome to my channel Lesson Physics. Today I shall discuss how to measure EMF of a cell with the help of a potentiometer, then how to determine low resistance of the order of few ohm or to fraction of an ohm with potentiometer. Before going to the details of the experiment, let us first discuss the components used in this practical. This is the resistance box. When a plug, these are the plugs, black plugs. When a plug is taken out, then that very resistance is included in the circuit. When the plug is inserted in the gap, resistance of that gap is 0. Because resistance coil inside the gap is short circuited. However, suppose two plugs are taken out, resistances marked as 5000 and 2000, that is total 7000 ohm is inserted in the circuit. Binding screws, these are the binding screws, are connected to the relevant portion of the circuit, say battery or any part of the circuit. This is galvanometer. Inside this galvanometer there is a coil which is placed in between pole pieces of a permanent horseshoe type magnet. When current flows through this coil, a magnetic field is created, and this magnetic field along with the magnetic field of the permanent magnet causes coil to deflect, and this needle is connected to the coil, so needle is deflected. Suppose the current is entering through this red binding screw and emerges through the black binding screw. So if at that time deflection is in clockwise direction, if direction of the current is reversed, that is it enters to the black binding screw and emerges to the red binding screw, then direction of the current through the coil will be reversed and deflection will be in the reverse direction, that is anti-clockwise. If there is no current through the coil, that is the galvanometer, then there will be no deflection and the needle will point 0 position, null position. This is called null adjustment. This is two-way key. I will discuss it later. This is the potentiometer. This is a horizontal wooden box or board. This is horizontal wooden board, but it is shown vertical for better understanding. Watts of uniform cross sectional area, capital A, say, are fixed parallel to each other and connected in series. They are fastened through these copper strips and they are made up of constant and watts. The resistivity of the constant and watts are 48.2 into 10 to the minus 8 ohm meter, whereas the resistivity of the copper strips are 1.68 into 10 to the minus 8 ohm meter. Since the resistivity of copper is much less than resistivity of the constant, so the total resistance of the constant and watts are much greater than the copper strips. So in calculation of resistance, we can neglect the resistance of the copper strips. The watts are fastened here, and also in the opposite side they are fastened in this way. So they are connected in series. There is no connection between these 2 points. These going in this fashion, coming in this fashion, again it is going in this fashion and coming in this fashion. So they are connected in series. There are 10 watts, 1 2 3 4 5 6 7 8 9 10, each of length 100 centimeter. This is a meter scale, so length of the each wire is 100 centimeter. So total length of the potentiometer wire at 10 into 100 centimeter, that is 1000 centimeter. This is key. If the plug is inserted, then current will flow. If the plug is taken out, current will cease to flow. This is ammeter. The basic principle of ammeter is same as galvanometer, because ammeter is nothing but a galvanometer with a low resistance in shunt. This is the positive terminal of the ammeter and this is the negative terminal of the ammeter, and at this moment it is giving a reading of 3 ampere. Okay. Function of two-way key I will discuss later. This is the circuit with the help of which we will determine the unknown EMF of this battery. This is the driving battery whose EMF capital E is known to us. This is the resistance box, and suppose the resistances marked as 5000 and 2000 are inserted in the circuit, that is these two plugs are taken out. So this is the circuit. Note that negative terminal is connected to the binding screw of resistance box. Here, for simplicity, I have omitted commutator. There is a commutator here which reverses the direction of current. I have discussed the function of commutator in a separate video, so I have omitted this commutator here for the simplicity of the discussion. Suppose capital E is the EMF of the driver battery. So this driver battery, this is the positive terminal of the driver battery, which is connected in series with the ammeter, and this current flows in this position, that is at the point M, positive terminal of the battery, driver battery, as well as the positive terminal of the battery whose EMF to be measured are connected. This is very important. This is the M point of the potentiometer. This point M, this is the point M, and this is the other point of the potentiometer S. Look, this is the other point of the potentiometer S. Here I have taken only 4 watts for simplicity. Actually there are 10 watts as I have told earlier. So this battery is connected between the point M and S. Total resistance of the potentiometer wire, say it is Rp. Resistance of the potentiometer wire, say it is Rp. So then total resistance Rp is included in this circuit, and say R prime is the resistance, that is sum of the resistances 5000 plus 2000, that is 7000 ohms, say R prime. So EMF of this battery is Z. So this current I is nothing but E divided by this resistance R prime is in series with this resistance of the potentiometer wire. So the current is R prime plus Rp. If E is known and Rp is measured by the post office box or multimeter, then there is no requirement of the ammeter. You can calculate current I in ampere. But if E and Rp is unknown, you can measure the current with the help of ammeter. In any case, capital I is sending this driver battery and it is passing through this circuit. Now, the EMF of the unknown battery, say it is small e, and 2 positive poles, this is the positive terminal and this positive terminal, both are connected at the same point M. This is very important. And negative terminal of this battery is connected to the galvanometer to the jockey. This is called jockey. Suppose at this point, at this moment, jockey is connected at N, and at this position there is no deflection of the galvanometer. But before that, suppose at a certain moment, this is the position of the jockey and we are getting a deflection. Why? As because suppose jockey is touched at N prime. Length, and hence potential drop is smaller than N, because this length, suppose this is the position of N prime, so that length is smaller than the length at N. This is another point, N double prime side. So potential drop due to capital I is small and potential of E is larger. Potential drop due to I is now, say, instead of this battery, think about the potential drop across Mn prime. Suppose this is the battery with potential E.M.N prime. That's equal to current I into resistance M.N prime. This is the resistance of the wire between M and N prime. And this is the EMF of the battery, this battery E. As the EMF of the battery is now greater than E.M.N prime, current will flow in this direction, and this is the galvanometer. The current through the galvanometer is in this direction. Current is flowing in this fashion. Now, if instead of this point, now jockey is connected at N double prime, then the potential drop across the M and N double prime, say this battery is now E.M.N double prime. As the length is much greater than the N.M.N prime, we can think about the E.M.N prime is now greater than the potential of this battery E. Now E.M.N prime double prime is greater than E. So it will send a current in this direction and current will flow through the galvanometer in this direction. This is the direction. Now current will flow in this direction, anti-clockwise fashion. But previously current was in the clockwise direction as E was greater than this EMF. So deflection of the galvanometer in this case, if it is clockwise, so in this case it will be anti-clockwise. So there is a point N at which EMF of Mn is equal to EMF of the battery. Then no current will flow through the galvanometer and we will get the null point. This is the basic principle. Again, I am explaining this as it is very important. First of all, forget about this battery. This is sending current I and it produces a voltage drop across Mn prime. Say this voltage drop is E.M.N prime. So forget about this battery and consider this battery Mn prime, virtual battery Mn prime, Emn prime is the EMF of that battery, which is nothing but this current I into resistance between M and N prime, say Rmn prime. Since this length is smaller, this potential drop is small, then this potential, this battery is less voltage than this EMF, so E is greater. So E is greater than Emn prime. So it will send a current in this fashion, clockwise fashion. And galvanometer, through the galvanometer, this is the galvanometer. Note that this is galvanometer. So through the galvanometer is now from upside to downside. But in this case, when the jockey is shifted to N double prime, the length is much greater than Mn prime, and say Emn double prime, which is nothing but I into resistance between M, length of the wire Mn double prime, that is I into R Mn double prime, which is now much greater than the EMF of this battery. So this driver battery will now send a current through this battery and through this galvanometer. But this current is from downward to upward in this picture, so it is opposite to this previous case. So if in the previous case deflection in the rightward clockwise, it will be in the anti-clockwise direction. So in between these 2 points N prime and N double prime, there must be a point N for which the resistance Mn and drop across the resistance of Mn, which will create a battery voltage Emn that should be equal to the potential E. Now let us forget about all this position and just consider about the Mn. So what is Mn? Emn. What is Emn? Emn or voltage Mn, Vmn say, that's equal to I into Rmn. Rmn, resistance of the wire Mn, is nothing but resistivity of the wire, length Mn divided by cross sectional area A of the wire. Now what is Lmn? This is 100 centimeter. We can neglect the resistance of the copper, and this is 24 centimeter. This is 10, 24 centimeters. Say it is 76, so it is 24. So total length is 124 centimeter. So Lmn is known to us. So if we know rho, cross-sectional area of the wire, current is known, we can find out the unknown EMF of the battery. But suppose at this moment we don't know the cross-sectional area of the battery. So we can find out it in another way, alternative way. There is I is equal to, we know, E divided by R prime plus Rp. So potential drop across total length of the potentiometer, total length of the potentiometer wire is equal to E into Rp. Rp is the total resistance of the potentiometer wire. This is, so potential drop per unit length of the potentiometer, say rho prime, is equal to E Rp divided by R prime plus Rp into 1 by L. L is the total length of the potentiometer wire. Now what is the potential drop for the length Lmn? Then potential drop for length element of potentiometer wire is equal to clearly rho prime into element, which is nothing but, note that if E divided by R prime plus RP is the current and current is known, it can be written in the form ERP by L. So rho prime is I RP by L into Lmn, and this is nothing but the unknown EMF E. As because this potential drop across Lmn is now equal to the potential of the battery, otherwise there will be a deflection of the galvanometer. As there is no deflection of the galvanometer, it is null point, so these two potentials are equal. Now it is all terms in this case are known to us. I is known, RP is known, Lmn is known, capital L 1000 is known, so we can find out the unknown EMF in this way. So this is the basic principle of the potentiometer for finding out the unknown potential of a battery. With this idea, we are now going to find out the resistance X of a fractional resistance, say 0.1 ohm or 0.2 ohm or few ohms, 1 ohm, 2 ohm. That is very small resistances, and capital R is a large resistance in comparison to this fractional resistance. Say it is 8 ohm, 10 ohm, something like that. This is the circuit. The previous section between P and S as same as the previous picture, and new thing is that at this moment there is a two-way key. What is the function of the two-way key? Suppose at this moment we are connecting the 2 points B and C. So this point B and C are connected with the help of this plug. Plug is inserted, so B and C are connected. B and C are connected, and the plug between A and C is removed. So A and C, there is no current between A and C. A and C is open. So this is the path if a current flows through the galvanometer. So in the previous case, as is the previous case, if this potential drop, say for N prime, is small, then this battery will send a current like this, and a current will flow through the galvanometer. So in this case also current will flow in this path and a current will flow this galvanometer. But we are now discussing at the point Q, which is null point. So as discussed in the previous section, potential drop across PQ, or the potential between PQ, is equal to the potential across R plus X. Potential across R plus, now forget about this battery. It is giving a potential across R plus X. Since B and C are connected, R plus X is included in the circuit. This battery is sending a current I in this fashion. There is no current through the galvanometer, and as because the potential drop across PQ is same as this R plus X into I, this current I is also flowing in this section. So there is no current, no component of this capital current I in this section. So there is no current through the galvanometer, not due to this driver battery, not due to this unknown EMF or potential across R plus X into I. So as in the previous case, I into R plus X is equal to I into resistance between P and Q. Resistance between P and Q. What is the resistance? The length is 100 centimeter. Neglect the resistance of the copper wire, and this is 200 centimeter, 100 centimeter, 200 centimeter, and this is 82. So 100 plus 100, 200 plus 82, length is LPQ is L2 equal to 282 centimeter. This is null. And the resistance of the copper strips are neglected. So in this case, L2 is known, and I into R plus X is equal to this. Again, we remove this plug from this position and insert the plug between A and C. So now A and C are connected to this plug. Plug is inserted here, connection is there, but this plug is now taken outside. So there is no connection between B and C. So at this point, R into I, this potential, suppose this is a battery of potential Ri. Forget about this battery and consider this battery Ri, which creates a new null point, say at as because R plus X is smaller than R is smaller than R plus X, so it will take a smaller distance for null point. This distance, this length of the wire is smaller than the previous length of PQ. So say this length is L1. This plus this plus this is L1. So R P prime Q prime is I rho L1 by A, and this equal to IR. This is nothing but another battery. So forget about this battery. It is giving a current I, as because current starts from the positive of the battery and comes to the negative terminal of this battery. So always a current I is flowing, and in this path R plus X is inserted in both the case. At this moment, although the potential across R is measured, but the current I is same because this current flows through both the resistances R and X. So always the amount of current is same in both the case. I is equal to EMF E of this battery divided by R plus X in both the case. In this case, potential is E divided by R plus X into R, and the previous case it was E divided by R plus X into R plus X, that is E. So I is same in both the cases. So I is the same for the both the case, and this capital I is also same because this resistance R prime is kept constant. So this I is also same. R prime and the total resistance of the potentiometer are kept constant. So capital I is also constant. So if we divide these two equations, taking the ratio, we can find this equation. R plus X divided by R, I cancels out. This I rho by A and this I rho by A cancels out. This is L2 by L1, giving X, the unknown resistance, equal to something like that. Now the question arises, why we don't take only X, which will produce a voltage Xi, and we can find out in this way. This is because X is very small. So if we take only X, it will create a null point at this point, say. So this length is very small. It will, the length being very small, there may be some error in measuring this small length. But in our previous cases, the lengths are very large. it is taken at the 10th wire or 9th wire, so that the lengths are 900 or 800. So this is the reason for which this method is adopted. A large resistance R in comparison to X obviously is connected in series with X. This is the beauty of this experiment. With the help of this circuit arrangement, we can find out a small resistance with the help of potentiometer. The basic principle of the potentiometer is this: when null point is achieved, when null point is found out, then the potential across Mn is, due to the driver battery, due to the current capital I, is same as the EMF of this unknown battery. Here we can think that there are two batteries, one of potential Ri, another of battery R plus X into I. First time we connected this battery of EMF R plus X into I, giving null point at L2. At the second time we are inserting another battery of EMF Ri in the circuit, which gives null point at L1. So equation is something like this. But the basic principle is same as this. When null point is achieved, the potential drop across Mn due to the current capital I of the driver battery is equal to the EMF of this unknown cell. If it is not, if the case is this or this, current will flow through the galvanometer. I think it is clear to you all. And lastly, this is last but not the least, it is very important, we can measure any potential difference with the help of voltmeter. Why we are using potentiometer? Note that voltmeter cannot measure EMF of a cell. We are measuring EMF. Voltmeter measures only potential drop across the battery. What is the potential drop? What is the difference between potential drop and EMF? This is nothing but EMF is E. If internal resistance of the battery is smaller, then potential difference is equal to EMF minus I into internal resistance. So due to the presence of the internal resistance, voltmeter measures only potential difference. It cannot measure EMF. But in the case of potentiometer, we are finding out we are measuring all parameters in the null condition, that is I is equal to 0. As because at the null condition I is equal to 0, that is current through this battery is 0. If there is a current through this battery, there will be a deflection in the galvanometer. If there is any current I through this battery, there will be a deflection in the galvanometer, as shown as it is discussed here. But here I is equal to 0. So IR, the internal resistance R, and I is equal to 0. As a result, as because IR is 0, in this case EMF is equal to potential difference. So with the help of this, we can measure the actual EMF of the battery. We are measuring the actual EMF of the battery. I think it is clear to you all. Go through this video again and again. It will make clear. It will for clear conception, it is very important. Thanking you for for your patient hearing.